So, welcome everyone back for the second part of the morning session. So, even if it's written in the name of this conference that it's an XML conference, we welcome a lot of other contribution, and especially from our semantic fellows. And here we have a presentation on DBpedia by Sebastian that is well-known and representative of DBpedia community.
It's not, no, yes. Okay, no. Can you, yeah, I think it's working, I'm hearing it. Okay, so my name is Sebastian Hellmann. I'm from Leipzig, where I have a competence center at the Institute for Applied Informatics. It's called KILT, Knowledge Integration and Linked Data Technology. My profession is probably a knowledge engineer, so not a data scientist or data artist, or however you would call it, but more a knowledge engineer, so somebody who has engineering processes to facilitate knowledge. I'm here in the role as the executive director of the DBpedia Association, which tries to coordinate kind of like the DBpedia community. And I'm going to present our, like the things we have worked on in the last 2 years maybe, including our new mission, which is the global and unified access to knowledge graphs. So here is a DBpedia strategy overview. So as a starting point, you could say that DBpedia is the most successful open knowledge graph. However you want to quantify this, but so it kind of like was a knowledge graph already before the word knowledge graph was pushed by Google. So it exists since 10 years. We have seen Freebase come and go. Now Wikidata is coming. Yeah, but we're still very successful, even more so now that Wikidata is there. So the kind of like the greater publicity realizes that this is a very important topic. So what's the state? So we have 20 million hits daily on all different APIs, text linking, and the main database. 400 developers and researchers who do qualified contributions. Inlinks by all major data sets, then 4,000 website visitors weekly. The files we publish are downloaded 0.6 million times per year. And there are hundreds of interfaces and applications. And what's also very important is that we have over 20 language chapters. And especially I would like to mention the good work of the Czech DBpedia chapter, which is available under cs.dbpedia.org, which concerns with open knowledge in Czech. So now, what is the strategy? We're going to take DBpedia to a more global level, like scale up to create a global DBpedia platform. So at the moment, we were concentrated a lot on publishing content or data, and now we're going to make it into a platform, which means that third parties can interact together. So you share the effort of open knowledge graph, governance, collaboration, and curation, going to maximize societal value and also bootstrap a linked data economy there, or more general, a data economy if you want. So the medium-term goals are that 200 organizations share their data via the platform, then 50% of computer science researchers upload data, 10 million of users, and then 25% contribute back, and thousands of new businesses and initiatives around the data. So short history, when it started in 2008, the description basically said what we did. So DBpedia is a crowdsourced community effort to extract structured information from Wikipedia and Wikidata and make this information available on the web. So it's about publishing cool data, cool free data on the web for everybody. 2018, we had a lot of, like in the last 2 years, we had a lot of discussions. So because so the definition describes what we do, but not where we want to go, right? So the new mission is kind of like to have global and unified access to knowledge graphs. So the original definition still holds true, but it's not a mission statement. It's more a description of what has been done in the past. And then there's this matchmaking platform to integrate your data with all other data. So DBpedia already allows access to other data sets. You can see this LOD cloud here, which is published in a web-style fashion. So it's a scale-free graph, like in the World Wide Web. But this structure is very inconvenient for data. So let's say you have your databases here, and you have information about Angela Merkel, and then you want to know who else has data about the same person, same entity, and then you start following the links, right? So you have to crawl the whole network. Basically, this is what all the big web crawlers do, Google and Bing and whatnot. It's very difficult to build a web crawler. And finally, you might arrive here, and then you see, okay, this data that he has is not so good. I need to search more. But since the data sets or most of the data sets are already linked to DBpedia, the ways to do this are quite short. So you can have your database here, and then you can query DBpedia to see who else has an identifier representing the person you're looking for. So this is the hub idea. In the end, it's not yet there yet, because at the moment it's only in links, but we are working on the outlinks again as well. So we have some outlinks, but it's a bit of an asymmetric situation still, but it already helps a lot for data integration, because you can, if you have an identifier here, and the same identifier here is linked to DBpedia, you can assume that it's the same entity already. So here's how the DBpedia is created. I'm going to show an example of the Czech DBpedia interface of Prague. So the right side is copied from Wikipedia, Czech Wikipedia Prague. You see that the info boxes on the right side are already in a key value situation here. So you have the entity as the website, Prague, the city, and then you have the keys or the attributes and then the values. And this directly relates to the triple model. So you see that you're looking at the Prague information, and then you have the key value situation here as well. So the triple model fits quite well on this. This on the right side is then the structured information. So you can query over the whole Czech Wikipedia via DBpedia. So I'm going to present the different dataset groups that we are publishing. So these are kind of like the available extractions. So in total, if you run them all in full, you would receive 13 billion facts, around 200 gigabyte of data from all Wikipedias and Wikidata and Commons and maybe other sources as well. So there's a generic extraction, which is done automatically. Then mapping-based extraction, which is rule-based. Text extraction, which concerns the text, and the Wikidata extraction. And these are based on the Wikimedia XML dumps, which are published frequently. So let's look at the generic extraction. This is available in 132 languages. It produces around 30 data sets. Maybe you can look a bit at it. So you see here, if you go on edit, you see these values here. And the generic extraction basically takes the left side as is, and the right side, it has some optimizations for numbers and dates and normalizations. So if you go here, you can see that in the Czech DBpedia on the same page. Oh no, this is the English DBpedia. You have all the values here, which are extracted as is and a bit optimized automatically on the right side. And overall, there's quite a lot of extractors that have been created in the last year. So I'm showing you the extraction framework, which is licensed under Apache 2, so everybody can use it. There are also 235 forks, and Yahoo used it, and every a lot of people have their own extensions, and these are the ones that have been committed. So everybody, every extractor here, every class extracts a certain part of the Wikipedia page automatically. The next thing is the mapping-based extraction. These are only available for 40 languages, and it produces only 6 data sets. It uses the DBpedia org ontology property, so there's a clear schema in the background. And you can see here, so I made a grep out of this. So you see here, for example, on top there are coordinates. On the bottom there are this area urban KM2. And then we have these mappings that basically maps this value here with the underscores, which is has a very high heterogeneity in Wikipedia, to this ontology term. And it tells the parser that these should be typed as square kilometers. And here's here's another template which kind of like analyzes the geocoordinates sub-template. So this is a template in a template on Wikipedia. But it's very hard to extract this information automatically. So it's easier to have a large community, around 250 people who write these mappings once and then kind of like adapts them with Wikipedia. So the text extraction extracts 132 languages as well, produces in total 8 data sets. The most popular ones are the short and the long abstracts. These are also the ones you see when you use Google, right? So Google also crawls them. And we also provide them for free, so you can, if Google doesn't give them to you, you can download them from us. There's text mining training data extracted and also fact extraction, although this is more experimental. At the moment, these are currently offline due to maintenance, so we are doing a large refactoring. I'll talk about this later. Then there's this Wikidata extraction, which sounds a bit strange. So Wikidata is the Wikimedia approach to manage their own data and even and beyond that, so that the info boxes are replaced. They have more structure. They can use it as an internal database. But we still call it extraction, so it's basically the same approach as for the Wikipedia extractions. We have a generic extractor and a mapping-based extractor. The mappings here are used in JSON, so you just define these rules which bring them into ontology properties. So in the dataset, kind of like, so this extraction allows kind of like unified access over Wikipedia and Wikidata as a whole. And Wikidata, for example, has no ontology. It's a loose typing system. And DBpedia, for example, has eight ontologies. So the DBpedia ontology, Yago, Ambel, lots of community contributed ontologies. And yeah, this greatly helps with access and structure. And the generic extraction still extracts these 584 million facts from Wikipedia. So the adoption of Wikidata into the info boxes is not so it's going very slowly at the moment. So as a summary here, yeah, overall these are very rich data sets. Basically the knowledge of the world in the database. What the use cases normally are for companies that they use them either to structure their own data or they use it for enrichment for their search. So these are the main industrial use cases. I have to say that although the data is quite good, it only covers the things that are in Wikipedia and Wikidata at the moment. So it's quite limited. It will not cover every store or so, or every business or every street or something like this. So it's free and open data. Not even registration is required. CC BY license. highly available, so the downloads are on a Tier 2 server by the computer center of University Leipzig. Very good download speed. And we have this 7 million queries to the main database, and it has a 99.9% uptime, and you can build applications on it. So the database vendor Virtuoso from or OpenLink, who does the database Virtuoso, they maintain it themselves, kind of like as their flagship prototype, and they're very proud of it. So yeah, use it. And then what we have is we have this open community. It's very large and also very diverse community, especially the 20 language chapters. So there's Korea, Japan, Brazil, which all work on different topics. Politically positioned, so Google per se has a very high stake in Wikipedia and Wikidata because they're using the content there extensively. So you can imagine that the Google knowledge boxes during the search, they are almost the same as the Wikipedia boxes. We actually built this before Google, so we built a prototype based on DBpedia that had these knowledge boxes with a simple Lucene search to display the data back then for the telecom. But it was never published, so it was an internal project, and then 3 years later, Google had them as well. So if you compare the manpower of the DBpedia community, it should be in the same magnitude as Google. So they curate their knowledge graph internally, but here it's like a decentralized, diverse community of contributors. But the manpower should be the same. So this concludes kind of like the first part of the presentation. It's the current state of DBpedia. Any questions for this? Because I have a second part.
Thank you.
I have a second part.
Yes.
Yeah, actually, I have.
Take a question now or
Later.
Okay.
Just okay, I probably need to hurry a bit. Okay. So our new thing now is because the community is very so. This is the kind of like the new teaser here: knowledge graphs built by robots, and so I wanted to show you this cat picture. Yes, I'm showing you cat pictures. So this is kind of like the legion of data professionals that wrangle with the big data yarn. And you can see that I always find the expression big data quite strange because these are AI people and they are not knowledge engineers. So they focus on completely different methods and extensions. So yeah, probably don't have so much time. I'm going to skip some of that. Okay, maybe I can do it. So there are data challenges. I'm going to go over them real quickly. So first of all, there's this full duplex challenge. So data is not oil. You hear the term "we build a pipeline" a lot, but it's very bad methodology because actually you need something like upstream or sink, like a pipeline in 2 directions. So this is one challenge. We publish these 600,000 files, and then we don't have a way to get the changes of them upstream. There's this mapping reusability challenge. The schema mapping you have been doing last week, other people have done that before 1,000 times, but you cannot reuse the work of them. And then there's this metadata challenge for finding data. So generally, data processes are not yet well understood. So the only reference points I found is the Shannon model, which covers communications. This is from the 60s. And then GUA attempted to contextualize data better with this MCF XML format, and then later with RDF. So RDF is the format, and linked data is kind of like a way to publish RDF. RDF is kind of like fine, but linked data really has a lot of weaknesses. So there's the DCAT standard for the data catalog standard from the W3C, but it's a bit smelly because it was published, but now over 10 extensions already exist, which is a kind of like a bad sign for a standard. And then there's normally also the data registry failure. So we tried to upload DBpedia to a lot of repositories, but it was not possible to capture the complexity of it. And in general, there's a huge lack of discoverability. As I said, you can see maybe the linked data cloud, but you cannot download the data. So these were kind of like the data challenges, and then there are these system challenges which we had in the past. We had a big project called Align that was trying to align software and data engineering. And there's also a good book which was the result of the project. The main thing we found out here is, so we have been quite good at quality in DBpedia, quality refinement, but we were very bad with agility, the way and process that we published and extracted data. So we worked on this during the last year to improve it. So the lessons learned here from the project were we need a better dataset model. So you need something like abstract dataset identity and versioning. So also what we learned is data behaves like software on a system level. So you have schema and data changes which can break your applications. Data has its own life cycle. And you can also implement test-driven data engineering. On the other hand, data does not behave like software on a curation level. So it's Pareto efficient. So you start editing, you get 80% quality very easily, and then the last 20% is really hard. So you will never find the last error because you will run out of manpower. And derive is the main operation. Yeah. Derive is the main operation there. Lots of people say that they want to make a Git for data, but in my opinion, this does not make sense. So it expresses the desire to work better with data. But in the 10 years I've worked with data, I've never had the need to fork, branch, or merge a data set. It's not like software where you merge the same thing into itself, but more you have 5 data sets and then you integrate them. That's the standard use case. It's very rarely that you have kind of like the same version which you need to merge. So what we finished last week in the first version is something called the Databus. So Databus is the fancy marketing term, and then digital factory platform is what it is. So that's the definitory term. It's available under databus.dbpedia.org, and it was inspired by the Maven repository. So it's a data repository that works like a software repository. So the digital factory platform is in a sense like this, that you have your data is organized in stacks of boxes, much like the Maven model, right? So you have a software artifact, and then you release version upon version. And then you can take the boxes. You just need to find the boxes, and then you can take them, derive something from the content, and then republish the boxes. So it's decentralized storage because it's not physical. It's actually a no-link data approach because the file format doesn't matter. So you can have PDF or PDF collection or structured data, CSV, XML, RDF. And storage is generally cheap. You don't need to host a service or a database. So it's a file system. So it's very loose on the data side, very strict on the metadata. So provenance, license, you need a private key signature to check in data. You have to adhere to the dataset format, and then there's a versioning component. And the build automation, so the build automation tool we created is a Maven plugin. It uses actually Maven. It's available as open source online. It's optimized for re-releasing the same files. So you kind of like think about what your data set is and how you want to release it in which cycle. And then you build these Maven artifacts, and you can re-release them time after time. Yeah, let's look at the website for a second. So yeah, it is a bit copied from, the design is copied from Maven Central. You can see the publishers here, which are more important than with software, right? And then you have the same, basically the same trail here. So DBpedia, then the mappings group, you have this artifact, and then you have the version. And in the background, you have a database, which you can query, give me the latest files, give me only the English files of this data set, or give me a certain version. So it's much like the dependency process if you include software artifacts in Maven. So there are 3 operations. Load means that you can fully automated load data in a subscription model, either take the version or take the latest. You can derive data, so this is an internal process. This means that you create a new artifact by conversion, filtering, extraction, text mining, enrichment, statistics, generating a machine learning model, fix errors, anything. So basically it's a new data set. And then we have the release process, which is the Maven lifecycle phases package and deploy. Here, package means that you publish the files on the network, so this means on your server. And deploy means that you upload the metadata for all your files into the Sparkle API. So the idea is on the network level, because we are dealing with the web of data, to turn this around. So the left situation is you have few benefits, high effort. What we're trying to do is you have less effort and good benefits, so kind of like an incentive model to publish open data and metadata on the web. Yeah. Okay, I'll make 2 slides and then finish. So loading here, fully automatic, so useful for any consumer. You can build applications on it directly as input for your app. So the Sparkle query is the parameter for example, this is an example, Dockerized databases. So if you find JSON on the databus, you can directly load it into MongoDB. RDF goes into Triple Store. XML can be loaded into ExistDBs. You can update it each month or so. It's fully automatically programmable. And then you would have some dependency declarations like this. My software uses Apache Compress, which is a Java library in this version, and then this data set to work properly because the newer ones changed their schema, so we cannot use the latest one, for example. Derive generally is the derive, which data set is derived from which is very useful information for reusability. For example, can you download DBpedia as XML? So you can query where was it derived from, so you would get the Wikipedia XML dumps. You would at least know where it comes from. But probably this is very hard to analyze. The query 2, for example, you can ask who derived from it. And then this is not loaded yet because it's so fresh, but there was a project, DBpedia as tables, which converts all the RDF into tables. So you would at least find the CSV variant of this data set. There are trivial operations, trivial derive operations, which are pushed to the clients upon download. For example, the format variant. TSV and CSV are isomorphic, so you don't need extra artifacts, and also compression is isomorphic. Okay, this is where you show you that you can really run the Maven commands. And then, so there's this, the Databus Maven plugin is available, open source. Software code was completed last week. We tested it on DBpedia, so 10,000 files have already been published with it. So snapshot is still a snapshot version, but hopefully stable in some weeks. User manually is work in progress. And then there's this website, which is a public metadata repository, not exclusive to DBpedia data, so anybody is free to use. The metadata is published under CC 0, and the published files have to stay on the publisher's server, so you have full control over access. For example, you do HTTP authentication and the license as well. So the repo software is not open source, but we are running pilots in companies, for example, Siemens, where they structure their internal data space according to the databus. Yeah. So now I'm finished. I'm just showing the DBpedia members here. Okay. Awesome.
So I think we have time for 1 or 2 questions, max. Okay. Okay.
If I have understood correctly, the files uploaded into the Databus are treated as opaque entities. That is, they have rich metadata, but you cannot look inside them. And have you not considered encouraging to have RDF representations? So you would have a second trail. You use RDF for Wikipedia, but then you could start to use RDF for the contents of your databus.
Yeah, of course, but so it's a platform. It means that other people can do such things. So that's a derive operation. So let's say you find CSV, you go ahead, annotate it as RDF, it's a derive operation, and republish it with the link to it. So people can find whatever you think is appropriate to describe these files, right? And I think that's the only way it scales, because otherwise all the work will be on a small team to do it. And so yesterday I met a researcher who did exactly this, like with descriptors and things like that. And yeah, maybe 2 weeks he will publish his files on this, so you can query his annotations on the content of the files. I think it's a scalable, decentralized system, right? It's also why we cannot host all the files ourselves, because it doesn't scale.
Thank you. Thank you very much.
Oh.